I will introduce the next one, the talk of Seshadev Padhi, a note of the eigenvalue criteria for positive solutions of a cantilever beam equation with free end. Okay, you're welcome.
So, in fact, I'm giving my outline something like this. We shall be considering a fourth order boundary value problem, and it is a 2-point boundary value problem. The 2-point boundary value problem, the boundary conditions, the local boundary conditions at 0 and 1 that models a cantilever beam equation where one end is kept free and the other one is fixed. And assume that the function f is a continuous function, and we use positive, absolute positive, and g also a positive function. It should be QG, and lambda is a parameter. The sufficient condition we obtain clearly that completely depends upon the parameter lambda here. So I'm going to explain this. So the entire work here depends upon here 5 to 6 papers I'm considering here, 7 papers. Gustafsson and Smith, they published a paper and they published a book by lecture note in 1975. That is methods of nonlinear analysis in the theory of differential equation. They published a fixed point or 2 fixed point theorems. These are really interesting, and that is somehow they are generalizing Krasnodolsky fixed point theorem, especially on cone compression and cone expansion theorem. But later on in 1977, Gatica and Smith, they published a paper in Journal of Mathematical Analysis and Applications. They improved the conditions there. They made some generalizations of the theorems. I'm going to explain them, the theorems. Let me give you an idea. I mean, to get an idea on cantilever beam equation and the number of varieties of boundary conditions there, one can refer the paper by Chaitanya P. Gupta that published in the year 1988 in the journal Applicable Analysis. Since then, cantilever beam equation that is attracted by many authors, especially this is a fourth order boundary value problem. And there he has explained around 8 different conditions there that depending upon the positions of the cantilever beam. And the method, we have used a mutual function BT in this work that came from the paper due to Iturriaga, Massa, Sanchez, and Ubila. They published a paper in Mathematics and Nacritas in 2014. Then the method was also applied by me, John Graf, and one of my colleagues, Ankur Kanojia, that worked, we published a paper on elliptic equations that depending upon a parameter. But there we didn't consider in eigenvalue criteria, just we considered the bounds on the parameter lambda there on an elliptic equation. The same method is applied in this work. And the equation what we consider here, the same equation is considered, but with different methods, especially monotone iterative method was applied there by me and one of my colleagues. Finally, the paper what I referred is Jeff Webb and Conlan. They published a paper, eigenvalue criteria for existence of multiple positive solutions of nonlinear boundary value problems of local and non-local points, non-local type, that published in methods in nonlinear analysis. No doubt, number of papers are there on fourth order boundary value problem, but these are the 7 papers what I have, which are the motivation for the present work. So, what we have done, we have demonstrated here the results of the papers of Gustafsson and the next by Gatiga to obtain positive solutions of the fourth order 2-point boundary value problem U4 prime t equal to lambda qt f of ut, the interval is 0 to 1, and u0 equal to 0, u prime 0 equal to 0, u double prime 1 equal to 0, and then triple prime 1 equal to 0. In fact, this describes a cantilever beam problem on the deflection of an elastic beam fixed at one end and other end is completely free. So a positive continuous function f is, and q is also positive continuous function. especially we can say non-negative, and lambda is a positive parameter. What we shall be doing, in fact, it has been obtained by many authors that if a boundary value, there are a number of ways of finding out solutions or existence of solutions. One of the method is upper lower solution method, and other methods, many methods are there. And one of the method is that transform the boundary value problem to an equivalent integral equation. So if one can transfer that equation, one can rewrite the equation, or we can obtain an equivalent integral equation, ut equal to integral over 0 to 1 gts qs f of s us ds. So if you hear that g, well, if lambda is there, we can put lambda here, but we can consider an equivalent integral equation if you consider like this. And if gt is a Green's function, then using the bounds of the Green's function, we can study the existence of solutions of this type of integral equations. So that's what I said earlier. The motivation for this present work has come from the paper due to Webb and Lan, the published in 2006, that is in topological methods and nonlinear analysis, one of the best paper I have seen on this. And a recent work by me, John Graff, and so on, that published in Differential Equations and Dynamical Systems in 2000. What happened? They studied the existence of positive solutions of this type of equation too. So intentionally, I have not written here the quantity lambda in equation 2, in the integral equation 2. Existence of positive solutions of 2 with an arbitrary and measurable Green's function GTS. That's what I'm going to give you, that how our results are compared with the results there. So I'm going to give a final remark at the end of this talk. So what we've done here, the idea we have taken from this, the motivation we have taken from the work of Ituriaga and our work in 2019, we have introduced a measurable function BT. That measurable function BT completely depending upon f. And by using the bounds on the first eigenvalue of the corresponding linear equation, we shall be giving different sufficient conditions for the existence of positive solutions of this equation, this boundary value problem 1. That's what I said you. The ranges in our lambda, in our theorems are completely dependent on the first eigenvalues of the eigenvalue problem. We shall be considering this work. Just after this slide, I'm going to show you. Many authors, recently Cheng et al., they published a paper in 2019, they published in a paper in Communications in Applied Nonlinear Analysis, where they studied a system of Hermitian type integral equations or Hermitian integral equations. These are the generalization of this integral equation, but the condition, they made the condition that G should be symmetric around G of TS should be equal to G of ST. This condition is required in the domain, what the domain they are considering. That is a bounded domain. We tried to avoid that condition here. So we have applied the technique applied by Webb and Lan, Padhi, that published in 2019, this is in 2006. And we have applied the eigenvalues and the corresponding eigenfunctions of a linearized integral equation corresponding to 2. So we shall see what we have done here. So before that, let me give some preliminaries. As I said, you 2 fixed point theorems are there by Gattega and Smith. These are the revised versions, revised version of the theorem due to Gustafsson and Smith. The first theorem was published by Gustafsson in 1975. The results are revised later on. They are revised by Gattega and Smith, and they published in Journal of Mathematical Analysis and Applications in 1977. These are the results. What happened? Suppose a Banach space is there and a cone is given to us. Inside that cone, define a region D that is bounded by the lines U equal to R and D equal to big R. Okay, so if you consider a domain D like that, U is in K, K is the cone in the Banach space X, such that R less than equal to nor mu less than equal to R. And if T is a mapping, it is an operator. If T is an operator that maps from D to K, satisfying this property, U is in D and nor mu, mu is less than 1, and it satisfies the integral equation U equal to mu TU, then it will never, the norm will not be or you will not be in the boundary of nor mu equal to r. Similarly, if mu is greater than r, mu is greater than 1, and u equal to mu tu, then nor mu will never be equal to small r. And this infimum over r is greater than 0, then we have a fixed point. So this should not be in the boundary. If mu is less than 1 and mu is greater than 1, then the corresponding integral equation with the parameter mu will never be in the boundary. They will not have any solution on the boundary. And then in that case, it says that it has a fixed point in D. It looks some sort of cone expansion, whereas this is looking earlier is looking just a version of a cone compression theorem of Krasnodębski, and this is a cone expansion theorem of Krasnodębski. It says that if you have Banach space and a cone, and a small r and big R be two real numbers with 0 less than small r less than big R, and if you have a domain D in the cone K with or bounded by the lines nor mu equal to small r and nor mu equal to big R, and if you have a compact continuous operator with the property that u equal to mu tu with mu greater than r, then it says that the norm of u will never be equal to r. And if u equal to mu tu with mu is less than 1, then norm mu will never be equal to small r. And this infimum should always be greater than 0, then it has a fixed point in the domain D. Inside the domain D, will be getting. So what we shall do, as I said, the equation 2 I have shown you that is an integral equation where I have not written any lambda there. Intentionally, it was not written there. In this work, we consider a Banach space 0 to 1 with the max norm that is given by 3, and we define a cone, positive cone we are defining. K equal to u is in 0 to 1, or k is in u is in x, such that this u is non-negative in 0 to 1, and define an operator like this. T of ut equal to lambda times integral 0 to 1 gts qs f of us ds, where this gts is the Green's function. It is given by like this: 1 by 6 s square into 3t minus s, where 0 less than equal to s less than equal to t less than equal to 1, and t square into 3s minus t for 0 less than equal to t less than equal to s less than equal to 1. Then it can be seen that a fixed point of this operator tu, fixed point, suppose t equal to u equal to lambda times integral 0 to 1 j of ts qs us f of s us ds with this bound with this Green's kernel satisfies the boundary value problem what we consider there. That is equation 1. So if you see the properties of the Green's kernel, it says that if g is equal to a square by 2, if I assume, and ct equal to 2t square by 3, a straightforward calculation, one can get the property 7. Ct into gs less than equal to g of ts less than equal to gs. That works for all t and s in 0 to 1. So since this inequality 17 is valid for any t in 0 to 1, let us consider the interval t is in 1 by 4 to 3 by 4. In fact, it has been seen, it has been proved, many results are there, that 1 by 4 to 3 by 4 interval is the best interval in 0 to 1. And if I consider the interval 1 by 4 to 3 by 4, the minimum of CT in the interval 1 by 4 to 3 by 4 is equal to 1 by 24. And in that case, this 17, the equation 7, the inequality 7 is valid for the interval 1 by 4 to 3 by 4 with this inequality. We will be getting this. G of ts is greater than equal to s square by 48 and less than equal to s square by 2. Here s square by 2 is gs. Okay, so here what we have done, in place of C2, we have replaced it by 1 by 24. In fact, this inequality, this property, this 8 helps us to obtain a cone that will be required to us, or it will help us to obtain the property that the third property, this third property of the fixed point theorem, so this will help us to prove the third property. So in most of the theorems, we shall be proving the property A and property B, first property and second property. We will not be going through the third property. So based on this, based on this, we will be getting the property something like this. What happens if you use a positive solution of the problem 1, the boundary value problem 1, then it is a fixed point of the operator T on the cone K, and the converse also holds. That's why I have written here, if ut is a positive solution of the problem 1, or ut is a positive solution of the problem 1, if and only if u is a fixed point of the operator T on the cone K. And at the same time, this ut satisfies this property. This helps as a load. Minimum of T is in 1/4 to 3/4 ut, that is greater than equal to 1/4 of norm mu. The norm mu is already defined here. In the Banach space, we have considered the maximum norm we have seen. 1/24 norm mu, it will satisfy. As I said the third property in both the theorems, since we shall be applying this theorem 2.20 and theorem 2.1, here the third property is required to us everywhere. Infimum of norm mu equal to R, norm of TU is greater than 0, and infimum of norm mu equal to R, norm of TU is greater than R. To prove this, we shall be proving a general theorem based on this lemma 2.1 is this, lemma 2.2. If f of t equal to strictly greater than 0 on this region, when for t is 0 to R 0 to 1, and u equal to 0, if R is greater than 0 is a real number. So then it says that this infimum for TU will be greater than 0. P is the cone, nothing but where this is this property on the cone K, this additional condition is satisfied. This additional condition is satisfied. This is that cone P. I have written here. So if ut is a solution of 1, or clearly ut is a solution of 1, if and only if TU equal to u. Since you assumed f of TU is greater than 0 and it is continuous, for every t is in 1/4 to 3/4, u will be satisfying for norm u equal to R. You will be lying in the region R/24 to R. This is because of the condition this. You will be satisfying in this region because of the condition this. If a norm u equal to R, if this is less than equal to norm u, so this is a bigger and this is your bigger. So ut will lie in the interval R/24 to R. So R/24 to R. So if I assume that P is the minimum value or infimum value for T is 1/4 to 3/4 and R/24 to R, and if Q is the infimum of T square QT, this condition is required to us, then it says that T of ut is greater than equal to this quantity. So obviously norm of TU we are getting is this quantity is this is Q. So T square QT, this Q will be coming out. F of TU is equal to the minimum value. If this is a P, if it comes out 3/4 minus 1/4, 1/2, 1/2 into 1/48. So lambda by 96 PQ. So what happened here, as usual, if I consider a linear operator, something like this, right now since U this is a linear quantity, no F is there. If I consider a linear operator, then we have a very beautiful property here. What is that? The existence of positive solution of 10 is equivalent to the existence of positive solution of 11. Fixed point of L in the cone K. That cone is already defined. That U is in X as that norm of, ut is greater than or equal to 0. The cone K. The Green's function GTS is measurable and satisfies this property 12. So applying this property and assuming that 0 to 1 x to the power 4 QS BS DS is finite, we can prove that this L mapping from K to K is a completely continuous operator and satisfies L of K is in K. So L is mapping from K to K. And with the above assumption, this is 12, we can prove already. In fact, Webb proved in his lemma 25 that there exists an eigenvalue and the corresponding eigenfunctions phi. So, but for this fourth order problem, we have proved this in a separate, this additional condition was required. Integral over 0 to 1 x to the power 4 QS BS DS is finite. So using this additional condition, suppose integral over 1/4 to 3/4 x to the power 4 QS BS DS is greater than 0. If RL is a spectral radius of L, then it says that this spectral radius is greater than 0. And there exists a phi, that is function, eigenvalue function, non-zero function, such that LP equal to RL into P. RL, this RL is nothing but 1 by that first eigenvalue lambda. So this is what. Here what I've done in our eigenvalue problem, here intentionally we have written, we have introduced one term BT. I'm going to use that later on. Where I'm going to use that, just in the first theorem we shall say that. So based on this Q and B, the function what I'm considering here is something that lambda 1 QB. So as discussed in the beginning, the main theorem of this section, this paper uses the eigenvalues and their corresponding eigenfunctions to provide inequalities on the function f of tu and the ranges on lambda for the existence of positive solutions of the boundary value problem of that nonlinear problem. So by the above theorem, what happens? There exists a positive eigenvalue, lambda 1 QB. Lambda 1 is the eigenvalue, but comma QB, this quantity is given to indicate that eigenvalue, lambda 1 QB. That is the inverse of the spectral radius 1, which we call the first eigenvalue. Let us denote P1 QB is the associated eigenfunction. Then clearly lambda 1 QB, lambda 1 P1 QB satisfy this property. What is that? That first eigenvalue, the spectral radius is positive, and accordingly, the eigenfunction is also positive, and lambda 1 QB L P1 QB is equal to P1 QB. That is L P1 QB equal to RL. That is 1 by inverse. So this is 1 by RL. That is going to other side. RL into P1 QB. We will be getting this property. Just we will be using this property. Just what happened here in our first equation. If you see our nonlinear problem 1.1, we have not used any function B. Now we are using that function B. What is that? Assume that there exists a continuous function B that is going from 0, 1 to 0 infinity, and some constant C and delta and R with C power greater than 1. Delta is less than R. I'm not defining small r just to apply theorem 2.1 and 2.2 or theorem due to Gatica and Smith. We will be obtaining small r using this delta such that f of tu is less than equal to btu for u is in 0 to delta. That holds uniformly for t 0 to 1. And f of t u greater than equal to c bt into u for norm u for u greater than equal to r uniformly for t is in 0 to 1. Then it has a positive solution lambda, positive solution for every lambda lies between this quantity. This is the first eigenvalue. C is greater than 1. Lambda 1 QB by C less than lambda 1 QB. In this round, for every value of lambda in this interval, this will have a positive solution. So to apply theorem 2, let us assume that we claim that if this property is satisfied, it has no solution with norm R. In fact, if it has any solution with norm R, then using the first condition, we will be get one BT. And by multiplying QT P1 QB of T, we will be getting this contradiction. So it has no solution with norm small r. Now the question is that we have to show that it has no solution with big R when u equal to mu tu with mu greater than 1. For that, what we shall do? We already from based on this delta we got one r. So we consider a set D. D is u is in case has that r less than equal to nor mu less than equal to r. The operator T, what we consider this is compact and continuous. And if I consider any r big R bar greater than equal to r, we can show that this problem u equal to mu tu greater than 1 for mu greater than 1 has no solution with norm r, right? Norm r bar. If this is not case, we'll be getting a sequence of r's greater than equal to r bar, and a sequence of points mu n greater than 1, and a sequence of functions we will be getting satisfying this property or satisfying this property. So if I use the second condition, by multiplying both sides of this equation by bt qt p1 qb of a t and taking the integration, we will be getting this contradiction. So these two contradictions says that we have one r, such for any r bar greater than r, this has no solution. No solution with norm r. That in the second condition is satisfied. Third condition we already proved in the theorem. So by theorem 2, the bound value problem has a positive solution there, because the fixed point of the operator T is a positive solution of the boundary value problem in the cone K. The second theorem says exactly the same way, but it is reversed here. F of TU less than equal to BT into U. Here we have assumed the for B is a continuous function. We have assumed as usual C delta and R. Mu C is greater than R, delta is less than R. And if satisfies this H3 and H4, then it says that this will have a positive solution for every lambda in between these two. If you see this, the problem, it says that we can give an example for theorem 3.1. If I consider a superlinear problem, something like this, lambda U cube, U0, U prime 0, U double prime 1, U triple prime 1 equal to 0. This is the first eigenvalue for the corresponding linear equation. And we have seen that this has a positive solution in this region. For C greater than 1, a constant quantity, it will have a positive solution in this region we will be getting. Similarly, for the second equation also will be, for the second theorem also we have, if you consider two constants, delta in 0 to 1 are greater than 1, and C equal to 1 by delta square, delta is in 0 to 1, then this problem has a positive solution for each R. And remember, this one is the first eigenvalue we are getting there. Later on, I got a mail from Jeff Webb a few months ago. He said that, Dr. Padhi, I fear that this may not be the first eigenvalue problem, or I may have some wrong calculations. I checked that the calculation comes to be correct. So I replied that to Professor Webb, but I have not received any reply so far for this problem especially. Now we will be consider the final stage. If you consider lambda equal to 1, then we get this equation. If you proceed as in the lines of theorem 3 with the previous two theorems, we can obtain this result. If f of TQ equal to lambda 1 QB BTU for this, and f of TU equal to C1 lambda 1 QB in BTU for U greater than equal to R, this is for U is in 0 to delta, then this problem has a positive solution. If lambda equal to 1, direct we will be getting. So we are not giving a region, regional lambda, but just we will be needing, what we will need is the first eigenvalue. The second theorem we have, if a B is a positive continuous function in 0 to R, 0, 1 to 0 infinity, and we have a C delta R and C greater than equal to R, satisfying these two properties H7 and H8, then it will have a positive solution. And the conditions, this 5, 6, 7, and 8, although they look something like this, sometimes it is easy. It will be easier for us to use conditions something like this. What is that? If limit supreme U goes to 0 plus, f of TU by U, satisfying this property, and limit infimum U goes to infinity, f of TU by U greater than equal to this quantity. Or if limit supreme U goes to infinity, f of TU by U is bounded by this quantity, BT into this quantity that holds uniformly. You can take this BT other side and limit infimum of this quantity. It holds uniformly for T is in 0 to 1, then the boundary problem has a positive solution. In fact, these two theorems, last two theorems are quite easy to see them. See in our eye how the condition they look. So since the existence of positive solution 1 is equivalent to the existence of positive solution of the integral equation, where GTS is the Green's function defined in 6, then our last two theorems, the last two theorems we have shown this. This can be applied. Remember, if you use this first eigenvalue, okay, these two last two theorems can be applied to any general equation, any equation, integral equation, where GT is a Green's function that satisfying the properties considered in this work. Webb and Lund, they proved some existence theorems for the general integral equations of the form 2 with general Green's function. He proved that the Green's function they should be measurable and satisfies the property 12. The property 12 is something not like this. I can show you this. I'm going to that. The Green's function should satisfy this property. It should be continuous at the point tau. So let me go to the final remark once again. Webb and Lund proved some existence theorem for the general integral equation of the form 2 with the general Green's function satisfying the property 12. They says that there should exist a subinterval AB in 0 to 1 and a function P and a constant mu They said that this condition is required always. Q phi is L1 in time integrable and Q is greater than equal to 0 almost everywhere, and this should be greater than 0. And G of TS should be less than equal to PS, and G of TS should be greater than mu times PS for all T in AB and almost everywhere S in 0 to 1. And F should satisfy the correct theoretic conditions. In fact, the Green's function we have obtained here, that automatically that satisfies all the properties with mu equal to 1 by 24 and P of S equal to G of S. So when VT equal to 1 and C equal to 1, our conditions what we get here, the result what we get in our theorems, they are equivalent to the conditions of theorem 3.1 for theorem 4.1 due to Webb and Lahn. In that way, we have obtained we have improved the result. However, the result what we have obtained here can be extended to a system of integral equations. So I'm working on this for the system of integral equations. Recently, one paper came, as I said a few minutes ago, in 2019, one paper came by Zheng et al. They published in the journal that is published by American Institute of Mathematical Sciences. Communications in Applied Nonlinear Analysis. They proved some theorems based on the condition that G of TS should be equal to G of ST. The symmetry condition is required. We are trying to avoid that condition here. If we can get that, we'll be getting more beautiful result. We're still working for that. Thank you.
Okay. Thank you very, very much. It was very interesting talk. And what questions do you have? In Zoom, we have no question, but in auditorium.
Yeah, but in auditorium we have question. So my question is, why are there exactly 1/4 and 3/4 of the segment as this problem?
We can prove the result. What happens here, since the result works for everything, the result can be working for any AB subset of 0, 1.
Yeah.
So the result that if you go for AB, T is in A to B. If you go for T is in A to B, I think A is the minimum value. We will be getting 2A square by 3 we will be getting. Yeah. Is that correct?
No.
Yes. When the minimum value of T is A here. So, and the result what we obtained here, that works for, here we have written this intentionally from 1/4 to 3/4. I've considered 1/4 to 3/4. We can obtain the result for A to B also, subset of 0 to 1. But it has been obtained, it has been proved. I don't remember the author, that is published in the Electronic Journal of Differential Equation, that published in the year 2015, I think, something like that. They said that the interval 1/4 to 3/4 is the best interval to get optimized result in place of choosing AB for any AB in 0 to 1. 1/4 to 3/4 is the best interval to consider to be considered in the interval 0 to 1. So I consider this 1/4 to 3/4, but we can go for what you say A to B. We can go for that also. But in order to use eigenvalues and eigenvectors, just I choose 1/4 to 3/4 for the inequalities. The inequalities, I can show you 1 minute, please. The inequalities I can show you. It might be looking very small. Here I have used this inequality. We can go for 1/4 to 3/4. There is no problem. Accordingly, this U norm U by 24 will be changed. And this for calculations, if I make A to B and so on, the calculation becomes much complicated and so on. That's why I have not done that. A to B. So I've gone for 1/4 to 3/4.
Okay. Okay. Thank you very much.
Very much.